So now we start to look at Eulerian fluid mechanics. And in this case, as I said, we're not going to follow a packet of fluid. We're going to study a space, a geometric position in space, and study how the velocity changes in that space. So the forces of Lagrangian mechanics still apply. That is, the fluid in this space can increase in speed because of pressure forces pushing on it. It can increase its speed because there's viscous forces acting in the different faces as well. But another thing that can happen with Eulerian that doesn't happen with Lagrangian is faster fluid can just come into our space. So if there's faster fluid, behind this fluid that just goes into our space, then that's going to increase the speed of the fluid in the space we're looking at. Similarly, if there's faster fluid below and there's an upward velocity, then that faster fluid coming up could enter this space and cause our velocity to go up. So we're going to be adding terms that take into account the ability of fluid from neighboring regions to bring faster moving fluid into our space. So let's consider first the momentum change if we bring faster moving fluid, from the y direction. So we have a rho du dt is equal to minus dp dx plus mu. Same thing we have above, c squared u dy squared plus d squared u dx squared plus d squared u dz squared. But now there's a possibility that this fluid here could be coming in from the v direction. So let's think about what this is saying. This is saying if there's a v velocity, that could bring a faster or slower moving fluid into our regime and therefore cause u to change. So if v is positive, that's going to bring, and d rho du is positive. Well, if d rho du is positive, d rho u dy is positive, that means that du dy is positive. And so that means that u is going to be faster in our space than in the space below. So that would mean that if v were positive, it would be bringing slower moving fluid into our thing, which is why we have this negative sign. So this negative sign is saying, look, if v is positive, so the fluid is moving up from below, up from the back here as it is, and then but du dy is also positive. That means it's bringing slower moving fluid into our space, which would slow our fluid down. So the same thing can happen in all the other directions. So you have this term, and then you have another term that allows that same kind of thing to happen in the z direction. So you have, again, we're doing the x momentum equation, so we're still interested in what's happening in the u velocity. But in this case, it's if u is faster if it's faster in our block than it is the block behind us in z, or below us in z, then if we bring fluid in from below, that's going to slow us down. Similarly, if if u is faster above ours and w is negative, well, that's going to bring faster fluid in. So if du dz is positive but w is negative, that's going to bring faster fluid in. So that's going to cause u dt to go up. And finally, of course, you have the same exact thing in u. So u d rho u dx gives you that term in terms of the x direction. So faster fluid moved behind brings faster moved fluid in, et cetera, et cetera. We're saying this is all for incompressible flow, so we don't need to carry these rho's around in these derivatives. We can rewrite the whole thing with rho pulled out, which we will now do. So we have rho du dt is equal to minus dp dx plus mu times those same second derivatives, d squared u dx squared, d squared u dy squared, d squared u dz squared. And then we have these three terms that say, look, yeah, also fluid could be coming into our space from neighboring spaces, and that could change our velocity in u. So these three terms say, look, it could, if you have a different u below in the x direction, then if u is positive or negative, that's going to bring faster or slower movement fluid in the u direction. If there's a gradient in u in the y direction, then if there's a v velocity, fluid will be entering or leaving from that direction. And if there's a difference in u in the z direction, then the w velocity will cause fluid to either enter or leave our space, changing our u velocity. So finally, the way you almost always see this for incompressible flow, rho is out in front. We have du dt, and then we have all these terms brought over to give them a positive sign. So we have u du dx plus v du dy plus w du dz. And then we have minus dp dx, and we have mu, and I'm just going to call this the Laplacian del squared u, which represents all three of these derivatives there. So that is the equation that you have for Eulerian incompressible fluid mechanics. So that's your momentum equation. This is the x momentum equation. That's why it's all u's here. Everything is u in the numerator because that's the x momentum equation.